All right, it's 11, so let's get cracking. Um, Today we're going to start our discussion on the review of essential electrical and mechanical concepts. So we're going to start by looking at stress and strain relationships. Doing the mechanical engineering type things first. So let's start by defining stress as the intensity of internal forces within a body due to loading. So there are two types of stresses that are typically observed in MEMS devices, and they are normal stress and shear stress. So let's start by looking at a structure under a load. So this is going to be our z-axis. Here's our x-axis. Here's our y-axis. I'm going to draw a structural member here. So we have a simple beam. Let's give it some dimensions. So it has a particular length. Its dimension in the x direction. It has a particular height. Its dimension in the z direction. And it has a particular width, which is its dimension in the y direction. Okay. So let's say that we apply a force along the longitudinal axis of symmetry. So let's call this force F sub x. Our beam has a cross-sectional area A, no, we'll talk about this more in a moment, over which the force is applied. So what is the vector direction of this cross-sectional area? Anybody know what I mean by that? X direction. Yeah, exactly right. So we'll call this AX like so. All right, just making sure you guys are okay with my silly little vectors and all that kind of stuff. All right, so the average normal stress will be defined as the magnitude of the applied force over a transverse cross-sectional area. Okay, so effectively, the direction of the force and the vector direction of the area are the same, or they're in parallel. Mathematically, the normal stress is given by this relationship. Txx is equal to Fx over A of X. So just a quick notational thing here. This first subscript is the direction of the area, and the second subscript is the direction of the applied force, just so you know where my subscripts are going to come from and all that kind of stuff, so that we're all on the same page. Now, some of you guys have a mechanical engineering background, and so you know that the capital letter T is not typically associated with stress. Instead, it's usually lowercase sigma, right? Well, because I'm an electrical engineer, sigma for me is electrical conductivity. So I use T for stress because I'm an electrical engineer, and we're going to use electrical conductivity. And unfortunately, we're going to have systems where we will have stresses and electrical conductivity in the same thing, like piezo resistors. So we literally can't just use the problem to tell us what T or sigma is going to be. So I have to make up fancy letters for quantities. So I just wanted to be clear about that. All right, so in general, the normal stress at any given point in a transverse cross-section of a loaded beam will not equal the average normal stress. This is just giving us effectively a representation or an average value of what's going on. So this is our first stress relationship. Now let's consider that we have a similar beam, but we load it differently. Okay. So here's my Z direction. That line isn't straight enough for me. X, Y, like so, same dimensions, which I did those in blue. And in this case, we are going to apply our force still going to be in the X direction, but we're applying it to an in-plane cross-sectional area. And so this is an example of shearing stress. So we're going to say that the average shearing stress is defined as the magnitude of the applied force to an in-plane cross-sectional area. So in this case, our cross-sectional area would be this top surface of our beam or member, and it has a vector direction in the Z direction. And so mathematically, our shearing stress will be given by the shearing T ZX will be Fx over AZ. And again, the shearing stress that we're calculating here is an average value, meaning that the shearing stress is not uniformly distributed over the area the force is applied to. We're just looking at a composite. Okay. All right, so what's the difference between these two things? Normal stress effectively is related to, normal stress is related to changing the dimensions of the beam or the member in question. And shearing stress is related to changing the shape of the beam, okay? And we can determine the intensity of the deformation by looking at what's called the strain, right? So let's see, how did I do this up here? Just a simple thing. All right. So strain will be defined. Strain is the intensity of deformations caused by mechanical stress. Okay. So both the normal stress and the shearing stress are going to have an associated strain. So let's start by looking at effectively normal strains. I should have just made a copy of this stupid picture since I'm going to redraw it over and over again. But let's look at this guy again. So we have our beam. If we apply some force in the x direction, what are we expecting to happen? Exactly right, a change in the length of the beam. So let me go to the next page here and draw another little picture. So we should expect our beam to experience deformation in the x direction for sure, because we're applying a force in that direction. So if I make a simple little plot here, here's z, here's x, and the y direction is out of the page. Before the force is applied, this is our what it looks like normally. After we've applied some amount of force, enough to cause some sort of elongation in the beam, this is what our new shape would look like, okay? So here is our force, still in the x direction. We have our initial length, and now we have some quantity delta L, okay? Because our beam has elongated. So our longitudinal strain is the relative change in length due to an applied stress where S is going to be the symbol that I use for strain. I don't even remember what the Greek symbol that's typically used is, but we also use it in electrical engineering. Okay, so lowercase epsilon, which would be the same thing as permittivity, which is once again completely used all over electrical engineering. So this is going to be delta L over L. And then we also have a transverse strain. So if we look at a different depiction, let's call this the z-axis. This is the y-axis, and out of the page is the x-axis. Prior to the force being applied, our beam has this cross-section. After our force has been applied, the beam has this cross-section, where this dimension is the change in width, and then this distance is the original width. This dimension is the change in height. This is our original height. Just for the sake of argument, our force is applied out of the plane, and yeah. All right, so we have a transverse strain, which is the relative change in lateral dimensions of a body due to an applied stress where we'll have SYY is the change in width over the original. SZZ is going to be the change in height over the original height. And these quantities have to be equal to each other. We'll talk about that in a moment, but it's related to Poisson's ratio. So if we apply a force at the end of this beam in order to extend it, we experience three different strains. We have a strain in the X direction because we are elongating the beam. We have a strain in the Y and a strain in the Z direction because the beam is deforming in those dimensions as well. Why does the beam deform in those dimensions? Why doesn't the length just increase while the width and height stay the same? So if we mechanically deform anything, does that change the density of the material? Not at all, right? So if this is a silicon beam, silicon has a particular density, 2,330 kilograms per cubic meter, I believe. That's a material constant, right? So it doesn't matter what the size of the beam is. If we stretch it, elongate it, or whatever, the density is the density. So if we have some original volume, the volume times the density gives us our mass, right? If we stretch the beam, does the mass change? Of course not, right? We're not creating or destroying anything, we're just changing its shape. So effectively, we have to experience all three of these strains, because if we change in one dimension, the other dimensions have to change in order to maintain constant mass for our beam, all right? It's as simple as that, simple logic there, okay. So this relationship that if we change one dimension, the other dimensions also have to change, is encapsulated by Poisson's ratio, okay? So Poisson's ratio is simply this fancy Greek V, whose name I can't remember off the top of my head right now, is negative SYY, so the strain in the Y direction over the strain in the X direction must be the same as SZZ, the strain in the Z direction, divided by the strain in the X direction. This is a material property of the structure the beam is made out of. Well, so if we elongate it, we should see that the other lateral dimensions get smaller. If we were to try to squish the beam, we should see that the lateral dimensions get larger. It's a V. That's a Greek V, which new. Mu. Okay. So I thought, yeah, mu, yeah, because I don't know why I was thinking it was eta, but eta is the fancy looking N. Sorry, yeah.
Yeah. Oh, yeah.
Yeah. All right. So these are our normal strains. Now let's take a little bit to talk about shearing strain. So shearing strain. Let me move this down one. Measures the change in shape of a body undergoing deformation. So we had our beam. When we apply that force to the surface, instead of having a profile like this, what we will get is a profile like this, where this dimension is our height, and then this dimension is our change in X. So our shearing stress, shearing strain, SZX, is going to be equal to the change in X divided by the height. So another way to think about the shearing strain is that it represents the extent of a rotational displacement, right? So if we had a beam and we push on this surface, we are going to try to rotate it forward. Or if we have a cantilever beam and we're applying a point force down, we're going to try to rotate the tip. Okay, that's all shearing strain is associated with. Stress and strain are closely related by a constant that is called the modulus of elasticity. Okay. So under small deformations, stress and strain are linearly proportional. So for normal stress and strain, we have the relationship T is equal to E S, and for shearing stress and strain, we have T is equal to G S. where E is Young's modulus. That should be a capital Y, excuse me. Measured in gigapascals, which is a material constant that quantifies the stiffness of a material, and G is the shearing modulus of elasticity, shearing modulus of elasticity. Measured in newtons per meter squared according to our textbook, but honestly, you could just call it gigapascals as well. It's force over area. 6 of one, half dozen of the other, okay? And it effectively measures how easily you can cause a deformation. Okay, so related arguably to the ductility of the material. These two constants are related to each other through Poisson's ratio. So we can say that G is equal to E divided by 2 times 1 plus nu. Okay. So both are material constants having to do with how hard it is to elongate or stretch a material versus how hard it is to deform or change the overall shape of the material. So now I'm going to draw 2 graphs. So over here on the left-hand side is going to be a graph for material that would be considered a ductile material. And it's going to look something like this. It's not remotely straight, my apologies. All right, so let's define a couple of things here. So this is going to be region 1. We're going to talk about that in a moment. Here's region 2. Region 3. And over here is region 4. This point is known as our fracture point. This most positive vertical peak here on this portion is our yield stress. This point here, where we're at our most positive, is what's called our ultimate strength point. And let's see, around right here is what we're going to call our proportional limit. And I'm going to continue this line up. Everything to the right of region 1 will be the plastic regime. All right. So, pardon me, my nose is itching like crazy. So region 1 is we're going to call the elastic region. And in the elastic region, stress and strain are linearly related by Young's modulus. So effectively, the slope of this line here gives us what Young's modulus is, okay? In this region, if the stress or applied force is removed, the material will return to its original shape, okay? So we can load our structure with a force over and over and over again. And as long as we don't go beyond this range, our material will return to its original shape, okay? Once we cross over into region 2, we have hit the plastic regime. Region 2 specifically is the perfect plasticity or yielding region. Stress and strain are no longer linearly related, and plastic deformation has occurred, where plastic deformation simply means that it's no longer going to go back to its original shape, okay? Region 3 is the stress hardening region. So in this region, the stress increases as the material elongates until the ultimate strength point is reached. So we're effectively putting the material under tensile stress, okay? And then region 4 is the necking region. So when we go beyond the ultimate strength point, a neck will form in the material where the local cross-sectional area becomes significantly smaller than the average cross-sectional area. The necking deformation is heterogeneous and reinforces itself as the stress concentrates. So effectively, it's a positive feedback system where the more we do it, the more necking occurs until finally the fracture point is reached and we have broken our material. Okay, so our sample has completely failed. So this is what we would see in a ductile material. So if I drew kind of a cross-section thing here, we put this thing under a strength test like we have over in Bogart Hall, we would find that our beam thing would look something like this, where this region where it's narrowing is effectively the neck. So our whatever material we had effectively became plastic, began to permanently deform until it was no longer able to keep up with that deformation, at which point it fractures and breaks. Okay. Transversely, we might have a material that looks whose stress strain plot looks something like this. So here is stress. Here is strain. This is characteristic of a brittle material, okay? We have one region. It is the elastic region. Our device reaches its fracture point, or our material might reach its fracture point before it yields and enters the plastic region. Meaning effectively, we can't deform it, right? We can elongate it to some point, so it does have some elastic properties, but it will not survive as a material with permanent deformation. So for something like that, if we put a beam in our measurement apparatus, we would find that it just breaks, but you could actually put it back together like a puzzle to restore the original shape. Okay. Glass is a brittle material. Silicon is a brittle material. Okay, so we're going to expect that we have to design such that we don't want any permanent mechanical deformations to occur. All right, so because silicon is an anisotropic material, meaning that specific crystal directions have specific material constants, we are going to have multiple values for our Young's modulus and our Poisson's ratio. So I'm going to give you guys a little table here. We're going to talk about, let's see, single crystalline silicon in the 100 plane, single crystalline silicon in the 110 plane, and we'll talk more about crystal planes and directions in our next class meeting when we talk about electrical characteristics. Single crystal silicon in the 111 plane, and then down here, polycrystalline silicon. Here we're going to have our Young's modulus measured in gigapascals. And over here, we are going to have our Poisson's ratio, which is unitless. Okay. So for single crystalline silicon, it has a Young's modulus of approximately 130 gigapascals. Single crystalline silicon is approximately 170. There's going to be 110 is 170, 111 is about 189. And then polycrystalline silicon, or poly, is somewhere in the ballpark of 160. These are not hard and fast numbers, just to be clear. Lots of different things can change these, doping, all that kind of good stuff, the amount of dopant concentration. So these are just going to be rule of thumb numbers. In the literature, you can see that these vary by as much as 25% in either direction. Okay. Similar thing for our Poisson's ratio. 0.25 roughly for 100 silicon, 0.3 for 110, 0.36 for 111, and then back down to 0.25 for poly. Okay, they'll also have different fracture strengths, but the range on that is so big that it's arguably not worth the point of giving some median value, because we're talking about the difference between 0.7 gigapascals and 7 gigapascals. It's full 10-fold order of magnitude that it's going to fall somewhere within that range. All right, now anybody have any questions about stress and strain and their relationships? Okay, great. Now let's talk about beams as springs. So in the macro scale, springs are typically coiled structures, right? But in a MEMS device, it's very hard to fabricate a coiled structure other than a planar coil. And so typically speaking, in a MEMS system, we use beams, micro scale flexural beams, as mechanical springs in both sensing and actuation schemes. There are 4 types of springs that are commonly used in MEMS devices: the extension rod, the cantilever beam, the guided beam, and a torsional spring. So I only got far enough in my notes to talk about the derivation of how extension rods and cantilever beams work. So we'll pick up the other 2 on Wednesday after I have time to write it out. So let's start with an extension rod spring. So the extension rod spring is simply a beam that is undergoing normal stress. So here's our Z direction. This is going to be our X direction. Let's consider the location X is equal to 0 to be our anchor point. Here is our Y dimension, and we have some beam like so. And I'm going to consider this length to be L, the original length of our spring. Actually, let's do that like this. This dimension to be delta L, so how much our spring has elongated. We are going to apply our force in the X direction, and this surface is our cross-sectional area. Okay. So using the relationship between normal stress and normal strain, we find that T is equal to ES. Okay. Our normal stress is what the hell happened? Is defined as the ratio of the applied force over the cross-sectional area. We have Young's modulus, and our strain is the relative change in length, like so. And so with a trivial amount of algebraic manipulation, we can find that our deformation, or the amount that our spring extends, is simply the applied force times the length of our beam divided by Young's modulus times the cross-sectional area. Okay. If we further manipulate our expression, we can find that the applied force, F, is equal to E times our cross-sectional area times delta L divided by L, which could be written as KE times delta L, where just putting this in the form of Hooke's law for small spring displacement, spring constant times the change in the spring length. Okay, so KE there, let me make sure that that E looks a little bit better, is the spring constant of the beam measured in newtons per meter. Okay. The higher KE is, the more stiff the spring is, and the harder it is to cause it to extend. Okay. So from this, we can say that KE, our spring constant, is simply E times AX over L. And we can express the change in length as simply the force applied divided by the spring constant of the extension rod. All right. So how do we make soft extension rods? So what I mean by that is, how do we get the largest amount of displacement out of a spring like this? Okay, so if we want delta L to be larger, that means we want its spring constant K to be smaller. For the spring constant K to be smaller, we need a long beam with a small cross-sectional area. Those are the design considerations in there. Simple, linear, proportional relationships. Nothing remotely hard about this type of spring. This is the simplest type of spring that we can ever possibly choose to use. Okay. All right, now let's talk about cantilever beams. Actually, before we do that, what would the strain be here, right? So there is some amount of strain that we can get to before our beam, in this case, will literally just fracture and rip off of its anchor point. The strain is literally just going to be the force divided by the cross-section area, because this is simple normal stress and normal strain. Excuse me, I think I'm messing up stress and strain relationships. I want the normal stress. Yeah. So that's just going to be the force divided by the area. So there is a limit to how much we can elongate this particular spring before we cause it to fracture. So just keep that in mind. Okay, cantilever beams. Math is going to be a little bit more of a pain in the butt on this guy. Cantilever. So a cantilever beam spring is simply a spring that's undergoing shearing stress. So here's our Z direction. What the hell happened there? Here's our Y direction. Here's our X direction. Let's consider this to be anchored at X is equal to 0. Here we have our beam. If we apply some force in the Z direction, and actually this is an axis of symmetry that's going to be important, so I'll go ahead and identify it. Let's see, we are going to observe a deformation. I'm exaggerating the hell out of this, like so. Where this Z here represents the amount of displacement the tip of the beam has undergone. And then let me try to do this here. So what I'm trying to pick here is the angle theta at which the beam is deflected from its rest state, okay? So for this particular system, the beam displacement is governed by a second order differential equation. E Young's modulus times I, the second moment of inertia, and I'll write this stuff down in a moment, multiplied by the second derivative of Z at some location X over the second derivative of X is equal to M at X. So let's unpack some things here. E is the Young's modulus of the beam material. I is the second moment of inertia in the direction of beam bending z of x is the displacement at location capital X along the beam length. And M of X is the bending moment. At location capital X. All right, so Young's modulus depends on the material, so that's just a constant that we look up in a table, etc. Second moment of inertia. So what does the cross-sectional area of most MEMS springs look like? What shape is it? Rectangular, right? It would be hard to do anything other than a rectangle. You could potentially have trapezoidal or something like that, but let's just consider a rectangular beam for simplicity's sake. So for a rectangular beam, the second moment of inertia, I, is equal to AB cubed over 12, where B is the dimension associated as a dimension in the direction of beam bending and A is the transverse direction of the cross-sectional area. So just for example here, let's draw a thing. All right, let me introduce a coordinate system. So this is going to be our Z direction. This is going to be our Y direction. And the X direction is out of the page. So let's call this the height. And this the width. Our second moment of inertia for this particular structure, where we're assuming bending is happening in the Z direction, is going to be WH cubed over 12. It's that simple. Now, if instead beam deflection were happening in the Y direction, we would have HW cubed over 12, okay? So the dimensions of our beams are going to be critically important because they're going to be related to our spring constants, as we're going to see. So if we were trying to make a accelerometer that only experiences deflections in one particular direction, what we're going to find is that we want it to be thinnest in that particular direction and then thick in the other direction so that it cannot deflect anywhere but the direction that we want. Okay. All right. Next page. So we'll get to that in a second, actually. So let's talk about our boundary conditions here because we're going to be solving a differential equation. Okay, so we're making an assumption here. At capital X is equal to 0, the anchor point of our beam, we are going to assume that our boundary conditions are fixed. So what I mean by that is that the beam cannot move at the anchor point and it cannot rotate at the anchor point. So The anchor point is solidly established. That part's not going to move. All deflection and angular displacement is going to occur further down the length of the beam, okay? All right, so if we apply a point force at location L, okay? So let me draw something here. So this is location L, the location at which our point force is applied, the bending moment M. So let's write this down. Our bending moment M of X is going to be equal to F times L minus X. So our bending moment depends on our particular position along the length of the beam. Substituting this relationship into our differential equation with our boundary conditions of 0 gives us EI times the second derivative of Z as a function of beam length, or where we're applying our force on a beam, over X squared is equal to F times L minus X. And with a trivial amount of manipulation, we can see that Zx is going to be F over EI times the double integral from 0 to wherever X of L minus X dx dx, or F divided by EI times L X squared over 2 minus L cubed over 6. So this gives us the amount of deflection that we experience as a position, or as a function of position along the length of the beam. Okay. Oh, goodness, sorry, my nose is itching so much. All right, so maximum deflection occurs at the tip of the beam where our position along the beam is exactly equal to L, the location of where we have applied our force, which gives us a displacement of FL cubed over 3 EI. We can rearrange this relationship to find that F is equal to 3 EI over L cubed times Z, and writing it in the form of Hooke's law gives us our cantilever beam spring constant Kc times our tip displacement Z. And from this, we can see that our spring constant Kc is equal to 3 EI over L cubed. Okay. So before we move along here, I want to compare these spring constants for cantilever beam and an extension rod beam. Okay, right? So for a cantilever beam, actually, Okay, so for cantilever beam, we have E times the cross-sectional area divided by the length of the beam, right? So we have an inversely proportional relationship between the spring constant and the length of the beam. Here, instead, we have 3E times I, where I is related to the cross-sectional area. All right, so let's go this out a little bit further here, right? So I is going, so, sorry, 3E width times height cubed over length cubed. Another way to think about this would be 3EA times the height squared over the length cubed. Are we okay with that, where the cross-sectional area is the width times the height of the beam? Okay, so we can see effectively that long beams make soft springs, but we need to have there is a relationship that's associated with the height as well. Okay, what's happening there? All right, so I just wanted to compare those two spring constants. Obviously, we can see they're going to be vastly different mathematical quantities, but we should expect to see that our cantilever beam springs are significantly softer than an extension rod spring for literally the exact same beam shape material, etc. Okay. All right. The angle at which the beam deflects. So the angle of beam deflection with respect to rest position is going to be given as theta of x. This again depends on where we're looking for it, is the first derivative of the beam displacement and this is going to be F EI times LX minus x squared over 2. At the end of the beam, the angle will be at its maximum. So theta at, sorry, that should be capital L. Will be equal to FL capital L squared over 2EI. Alrighty. And lastly, let's talk about stress. Okay. So during cantilever bending, the top surface of the beam is in tension, while the bottom surface is in compression. So we're looking at a portion of the beam close to the anchor point. We don't really care about what's going on out to the right. we have this axis of symmetry. And what we will find is that we have tensile stress up here, compressive stress down at the bottom half of the beam, where we're assuming that beam deflection was in the down direction here, and that these completely cancel each other out. Our stress is 0 along that horizontal axis of symmetry. And so what we'll find is that our longitudinal stress at a location ZX is going to be T ZX is negative M X over I times Z, where Z, capital Z here, represents our distance away from that center line. So capital Z is our distance away from our center line. Substituting in our expression for M, this gives us negative F of L minus X times Z over I. And we are going to wind up experiencing maximum stress at the surface of our beam at the anchor point location. And the magnitude of the maximum stress is given by FLB over 2I, where again, remember that B is the direction of bending. The factor of 2 comes about because we are at a distance of B over 2 from our center line to that surface. And expressed in terms of beam deflection, this becomes 3EB divided by 2L squared Z. So we can express the maximum stress in terms of the applied force or the beam deflection. Goodness gracious. All right, that is enough out of me for today. We're only wrapping up 6 minutes early anyway. Hayden, do you have a question?
Yeah, I guess. So sorry, just above that, yeah. Those questions.
No problem. Any other questions while Hayden drops us off? All righty, so we're going to talk about guided springs, which we might want to talk about spring combinations first, since the easiest way to think about a guided spring is 2 cantilever springs in series, so that I don't have to do all this terrible derivation again. We're going to talk about torsional springs, and then we're going to talk about a little bit about crystallography and the electric stuff that goes into this. And then we will be done with review and can talk about new stuff like noise and then actual devices. So I am done talking about stuff for the day. See you guys on Wednesday. So a guided, can I move to the next screen, Hayden? I mean, I'm also recording all this, just put it out there. So just as a quick thing, right? So a guided spring would be something like this. So let's assume that we have an anchor point here. I'm going to draw a dashed line here. And then over here, like this big thing right here is going to count as our mass, okay? So if we apply a force to our mass, what we're gonna see is that this cantilever spring, which is anchored here, is going to deflect in this direction. And then this cantilever spring, which is anchored here, is also going to deflect in that direction. So that we're gonna have something that has a profile effectively of like this. So this point right here, which is this large thick connection, we say that it's stiff enough that it can't rotate or deflect itself. So that's what I mean by a guided spring in a MEMS device.